Okay, I think it's almost time to start the seminar. Good afternoon, everyone. My name is Kyushu, Catalytic Material Transformation Division. Today, we are very happy to have the I²CNER seminar with Professor Shen from the Okayama University. Before he starts his lectures, I'd like to briefly introduce his background. Professor Shen received his bachelor degree from Jian-Ren University in China. I think it is a top university in China. And then he got a PhD from the from the University of Tokyo in the Department of Biology. After that, he got the PhD, and then he worked in the RIKEN about 13 years from 1990 to 2003. In RIKEN, he studied on the structure and function of the photosystem too. As you know, the water splitting reaction of the photosystem too is one of the most important reactions in Earth. It's extract electron and it's from the water to use the short fixation. In 2003, he then moved to Okayama University as a full professor. In there, 2011, he and his colleagues determined the high-resolution crystal structure of the photosystem too, and clearly demonstrated the catalytic center of the manganese center cluster. The result was published in Nature, and then how the research achieved was selected as the top 10, one of the top 10 breakthrough research of 2011 by the select most impact journal of science. He's now the professor and director of the Photosynthesis Research Centers of the same university. Today, the title of his lecture, Mechanism of Light-Induced Water Splitting in Natural Photosynthesis. Now, welcome, Professor Shen. Please begin your lecture.
Thank you, for your kind introduction and for your invitation to this seminar here. I'm glad to see so many young students. I hear that most of you are from the faculty or Department of Engineering, but the topic I'm going to talk today is related mostly with biology and biochemistry. So I will try to talk it as much as in detail as possible. But if you have any questions during my talk or after my talk, please do not hesitate to ask me. You can interrupt me during my talk. So, as Yusuf introduced, my topic of today's talk is the mechanism of light-induced water splitting in natural photosynthesis. Okay, thank you. As you know that our oxygen in the atmosphere is produced by so-called photosynthesis, by plants and algae, and we call it photosynthetic organisms. The process of photosynthesis is written here, which means that from carbon dioxide and water, and by using the energy from sunlight, and carbon dioxide and water is combined into carbohydrates and the organic substances we use, and then oxygen is produced in this process. So every year, the amount of oxygen produced by photosynthesis is estimated in this amount. So essentially, basically, all of the oxygen in the atmosphere is produced by this process. This gives you the turnover time of oxygen in the atmosphere to be 4,600 years. That means that every 4,600 years, all oxygen in the atmosphere is consumed by animals and humans, but the new oxygen molecules are produced by plants in photosynthesis. This time looks very longer, but if you consider the evolution of Earth, you know that the Earth was born about 4.5 billion years ago. At the time Earth was produced, there's no oxygen in the atmosphere, and the atmosphere is mainly composed of so-called reducing gas, in which carbon dioxide is the main component. Then after about 10 billion of years later, the first oxygenic photosynthetic organism, which is the ancestor of cyanobacteria we see today, is evolved. And from where oxygen is produced by the splitting of water using the light from the sun. Then the concentration of oxygen in the atmosphere increased gradually, but this process took a very long time. You see, through the full oxygen concentration we see today, it takes about 2 billions of years. Because of this increase in oxygen concentration in the atmosphere, it not only changed the environment of the atmosphere to an oxygenic environment, but also enabled the formation of oxygen ozone layer. Ozone. As you know, ozone is produced by radical action from oxygen and by illuminating oxygen with ultraviolet light. So, because of the accumulation of oxygen, ozone is also accumulated. These two factors totally change the environment in the land, on the surface of the Earth, which enabled organisms to evolve from seawater to land. And until about 4 to 6 billion of years ago, the oxygen concentration and ozone concentration reached to what we see today, and that formed the basis for the so-called explosion of species of organism, and from where the organism can move from sea to land, and which produced a variety of species, the evolution of species, many species of organisms from in the land. So this reaction is, we think it's very important, and we are very interested in how this reaction occurs, because as you know, water molecules are very stable and can never be oxidized or split without energy. And even today, the oxygen in the atmosphere is mainly produced by the natural photosynthesis. And this reaction occurs in a biological membrane. You see that in a leaf, within the leaf, there is a very complicated biological membrane, which is called, we call cytoplasmic membrane. And in this membrane, there are a number of membrane-protein complexes, one of which is photosystem 2. And this complex catalyzes water splitting and produces oxygen. So we are interested in the structure and functional analysis of this protein complex in order to see how water splitting occurs. If you look at the reaction itself, it's very simple. From two molecules of water, when it splits, it yield one molecule of oxygen and 4 protons and 4 electrons. And in the cells, protons provide the proton motive force across the membrane, which is then utilized by ATP synthase to synthesize ATP. And electrons provide the reducing power, and which is used to reduce NADP plus into NADPH. And these two compounds, ATP and NADPH, provide energy and reducing power to reduce carbon dioxide into sugars. And these sugars are used by animals and humans for survival. So this reaction provides energy required for most of the organisms to survive on the Earth. And the energy you see is originally from the light, which is from the sun light. This is visible light. Then the oxygen itself is not utilized for any photosynthetic cells. So in the beginning, it is produced as a byproduct of this reaction. But as I mentioned, this gradually changed the environment of the atmosphere. So now most of the organisms must require oxygen for survival. And so now we study the mechanism of this reaction, because not only of our interest in understanding, want to see this reaction, how it occurs, happens, but also because of the so-called artificial photosynthesis, the field of artificial photosynthesis. In the field of artificial photosynthesis, there are several approaches, but one of the major approaches is that if you can use water and visible light to obtain protons and electrons, then you may be able to utilize these protons and electrons, combine them again to generate hydrogen gases or even simple organic substances, like methanol. But the key for this reaction in the artificial photosynthesis is the catalyst. How you can obtain an efficient catalyst that is able to catalyze this reaction. As I mentioned, water splitting will never occur without the catalyst. And in order to show you how this reaction is actually happening, if you want to split two waters into oxygen and protons and 4 electrons in an aqueous solution without a catalyst, because this reaction is, in this reaction, 4 protons and 4 electrons are removed, the total reaction can be divided into 4 steps. And each step, there is 1 electron and 1 proton removed from 2 molecules of water. And when you consider the activation energy required for each step of this reaction, you can see in the first step, this is the most difficult one. It requires an energy of more than 2.0 electron volt. Then, if you consider energy from 1 photon in the visible light with a wavelength of 700 nanometers, 1 photon has an energy of 1.7 electron volt. So theoretically, this energy is not enough to drive this reaction. Of course, in order to drive a reaction, you need a higher energy than this energy in order to catalyze this reaction. And another problem with the aqueous solution is that each intermediate species generated during this reaction, there are many number of radicals, water radicals, oxygen radicals. which is so-called reactive oxygen species. And these species, ROX, reactive oxygen species, are very active and harmful, and if they are not controlled strictly, they will react with many molecules surrounding them, and in the case of cells, they will destroy proteins and destroy the whole cells. So in the photosynthetic membranes, this reaction is still catalyzed. In the presence of PS2, still proceeds with the 4 steps similar, but each step you see the energy required for each step is averaged and lowered to around 1 electron volt. Especially in the first step, the energy required for the first step is lower than 1 electron volt. So with this, 1 photon of the visible light has enough energy to drive this reaction. And this is the typical function of a catalyst. Then the intermediate states in this reaction, in the presence of PS2, is called S1, S2, S3 states. These states, they do not produce reactive oxygen species. Instead, they are some slightly changed catalyst. The structure of the catalyst is slightly changed during each step, so it produces several intermediate states, and which is a slightly different structure of the catalyst, which does not produce reactive oxygen species. So, with this reaction scheme, the water can be efficiently split into oxygen and protons and electrons in the cells. And by this process, the sunlight energy from the sun is converted into the form of proton, gradient, and reducing power, electron. So they are then utilized to fix carbon dioxide. So we are interested in the mechanism of this reaction, and especially the catalyst PS2, and how the catalyst looks like and how it functions to catalyze this reaction. So, as I mentioned, this reaction can proceed through this different intermediate states, and starting from S0, when 1 photon comes in, 1 electron and 1 proton are removed, which the catalyst then goes to S1, then to S2, and S3 to S4, and in the final step, it returns back to S0 with the evolution of 1 molecule of oxygen. So this reaction is a cycle, which we call a state cycle. This state cycle has been proposed more than 40 years ago, but the exact structure of the catalyst in this cycle was not known, because we have to analyze the structure of PS2, and this is what we have been done for many years. Because took us a long time, because PS2 is a very complicated and large membrane protein complex. And this is the protein composition of PS2. As you can see, there are 20 subunits in this complex, and among which 17 subunits are transmembrane subunits. These are the numbers of transmembrane helices. 5 transmembrane helices and 6, 5, and the others are 1 or 2 transmembrane helices. In addition, there are 3 hydrophilic protein subunits associated with the surface of the membrane. So, in total, it contains 20 protein subunits with a total molecular weight of 350 kilodalton. So this is a very large membrane protein complex, and in order to see the structure of the catalyst, we need to analyze the structure of this whole complex at a high resolution. So we have been purifying the protein from the cells and making the crystal. This is the crystal we obtained from cyanobacterial PS2. You can see the crystal looks very dense, dark, because it contains a large amount of chlorophyll. This is the pigment molecule that absorbs light in the plants. So we have been able to collect diffraction rate, spin rate from these crystals, which has the highest resolution of 1.76 angstrom. And we have been able to analyze the structure of this protein complex at a resolution of 1.9 angstrom. And this is the whole structure of the complex. And in its isolated form, it is a dimer. In the middle, it has axis dividing two monomers in left side and right side. And each monomer contained 19 subunits. As I mentioned, there are originally 20 subunits, but one small subunit was lost in the crystal. So each monomer contains 19 subunits, and a dimer contains totally 38 subunits. The total molecular weight of the dimer is 700 kilodalton. So this is a very large membrane protein complex. And this looks looking from the side of the membrane. And this region is the transmembrane region. You can see this is the outside surface of the membrane, and this is inside, we call the luminoside surface of the membrane. And these blue dots represent water molecules. So water are found in the surface of the two sides of the membranes. And in this middle region, because it is a transmembrane region, it is hydrophobic in the middle. So there are very few water molecules in the middle region. And most of the water molecules are distributed in the surface of the membrane, which are hydrophilic. And if we remove the protein backbones and just looking at the distribution of these water molecules, you can see they are typically distributed in the outside surfaces of the membrane. This is one of the features for membrane protein complexes. Then in this protein complex, there are a number of pigments and cofactors associated with proteins, which function to absorb light and transfer electron, and then split water into oxygen. And these are the arrangement of these cofactors. We call it electron transfer chain in PS2. In the middle, there are 4 molecules in green, which are chlorophyll molecules. And when light comes in first, one of these 4 chlorophyll molecules absorb 1 photon first, then 1 electron is ejected from one of these chlorophyll molecules. And this electron is transferred to a nearby pigment, which is phyophytin molecule, and then to other 2 nearby molecules, which are bound prostaglandins, we call QA and QB. And this then produces a charge-separated state. Electron is transferred to QB here, and then the initial chlorophyll molecule here becomes a plus cation ion. So this chlorophyll ion wants to receive 1 electron to be reduced to its initial state. And this electron is donated from a nearby molecule, which is an amino acid residue tyrosine of a protein subunit. We call it D1 subunit here. Then then this tyrosine residue wants to in turn receive another electron from a nearby molecule. And this electron is donated from here, which is a manganese 4 calcium cluster. Then after electron is donated from this manganese 4 calcium cluster, this manganese 4 calcium cluster needs to receive 1 electron from other molecules. And there are no any further molecules to donate electron to this metal cluster. So this manganese calcium cluster abstracts 1 electron from water, nearby water molecule. And when this reaction happens 4 times, 4 photons comes in and 4 electrons are removed from 2 water molecules, then the 2 water molecules are split immediately to produce 1 molecule of oxygen. And this is the whole process of water splitting. So, as you can see, the manganese calcium cluster is the direct catalyst for this water splitting. And we are interested in the structure of this manganese calcium cluster and how it catalyzes water splitting. This cluster is located in this region here. So this region is immediately in the immediate surface of the membrane in the luminal side. And it is covered by a large area of hydrophilic proteins. And this cluster is composed of 4 manganese ions. This purple are manganese ions and 1 calcium ion, which are connected by 5 oxygen bridges, oxo bridges. And there are 4 water molecules. This blue one are water molecules. There's terminal ligands. And 2 water molecules are ligated to manganese. This manganese is called manganese 4. And there are 2 water molecules ligated to calcium. And there are additional water molecules surrounding this region, but they are not directly coordinated to this metal clusters, but they form hydrogen bond networks to this cluster. This is the position of each atoms. We determined from the electron density of our X-rays diffraction gate. As you can see, we can clearly resolve the position of each atom in this cluster based on the electron density. And if we remove these 4 water molecules and turn this cluster around to this direction, to this direction, looking from here, this side, you can see it looks like a chair form, looking like this. But this chair form is distorted. It's not symmetric one. So this is, we call it a distorted chair form of the catalytic center for water splitting and oxygen evolution. You can imagine that if the chair is, because the chair is not symmetric, it must be unstable, not as stable as the normal chair. So this structure suggests that it is unstable, and because it has some instability, we think it is has some flexibility. It is flexible. And this flexibility is exactly what required for a catalyst for water splitting, because as I mentioned before, during the acetic cycle, the catalyst should undergo some structure changes in order to produce each intermediate state. And this has been confirmed by spectroscopic studies. There are many lines of evidence from spectroscopic evidence that in the intermediate state, the structure of the catalyst undergoes some structure changes, but we do not know exactly what kind of structure changes occurred during the reaction cycle. But from this structure, we can say that because this structure is distorted, it can easily undergo structure changes. And this is exactly what required for an efficient catalyst for water splitting. So nature has maintained this unstable structure in a protein environment in order to catalyze the water splitting. Then when we look at why this structure is distorted and look like a distorted chair form, why this is not symmetric. This is mainly caused by this in the bond lenses between oxygen and manganese ions. You can see the typical manganese-oxygen bond distances are in the range of 1.8 to 2.1 angstrom. And this is applies for 4 of the 5 oxygens from O1, O2, O3, and O4. All these 4 oxygen atoms have bond lenses to manganese ions as typical bond distance found in manganese oxide, which is in the range of 1.8 to 2.1 angstroms. However, this O5 oxygen has a very long, unusually long bond distance towards nearby manganese ions, which are in the range of 2.4, 2.5, and 2.6 angstroms. And this bond length is never found in inorganic manganese oxide. And this has been suggested that, not has been suggested. So this suggests that this oxygen 5 atom is in a specific position, different from the other 4 oxygen atoms. And because the bond length of this oxygen to nearby manganese is extremely longer, this suggests that this O5 atom binds weakly to the nearby manganese ions, and which in turn suggests that this oxygen may be easily cut out during the reaction cycle. And if you consider that for the oxygen formation, there are 2 oxygen atoms, and they must come closer to form an OO bond in the final step of oxygen formation. And this structure suggests that the O5 oxygen atom may provide one of the oxygen substrate for OO1 formation. Skip this. So, this structure suggests that the site involving O5 may provide a reaction site for oxygen-oxygen bond formation. And if we look, based on this, and we look for the second oxygen atom or water molecule that is close enough to O5 and may form an O bond between O5 and the second oxygen. There are 2 water molecules, here and here. We call W2 and W3. W2 is one of the water ligand, one of the 2 water ligands coordinated to manganese 4 ion, and W3 is another water ligand to calcium ion. So this region, both W2 and W3 have a bond distance, are within the distance of hydrogen bond between O5. So this region may form the reaction site for O1 formation. Of course, there are 3 oxygen atoms in this region, and we cannot still determine which 2 oxygen actually provided a substrate for O1 formation, because there are 3 possibilities in this region for 2 oxygen atoms to come closer to form an O bond. So what we have, we can do in this stage, at this moment, is that there is only one calcium here. The other four metals are manganese ions, and different from the manganese ions, the calcium ion cannot undergo redox changes, and the valence of calcium cannot be changed easily. So the manganese ions here are 3+ and 4+, and they can donate electron or receive electron from the water. So they are participating in the redox reaction of the water splitting, but this calcium ion cannot participate directly in the water splitting. And what is the role of this calcium here? We looked for the function of this calcium, and because why we look for this calcium, because fortunately we can replace calcium ion with another ion. The only divalent ion that is able to replace water, calcium and still support oxygen evolution and water splitting is strontium. And so this calcium can be replaced by strontium 2+. And after this replacement, the water splitting reaction, the activity of water splitting is decreased by half. But still it can catalyze water splitting, which indicates that the overall structure of this cluster can be maintained by even after replacement of calcium with strontium, but there must be some slight structure changes because the activity is decreased by half. So we replaced this calcium with strontium and made crystals again and analyzed the structure again. We see the activity in different preparations. In calcium and strontium replaced ones. The strontium replaced PS2 is almost half of the activity of that calcium PS2. And we analyzed the structure of strontium replaced PS2 and see what structure differences, structure changes have occurred. This is the diffraction pattern we created from crystals of strontium replaced PS2. And we were able to analyze the structure at the resolution of 2.1 angstrom. And we can confirm the position of the strontium here by anomalous diffraction, because strontium has a strong anomalous absorption peak in around 0.9 angstrom. And we used that wavelength to collect diffraction rate to see the position of strontium and this shown here, and this position is originally occupied by calcium. So we confirm that the calcium is indeed replaced by strontium here. And we compare the structure of the cluster in strontium and calcium containing PS2. There are several slight differences between two structures. One of the most significant differences is here. In the bond lengths between calcium and the two water molecules, water ligands, they are both 2.4 angstrom in the original native PS2, but in strontium replaced PS2, the bond length between the before and the strontium is the 2.3 angstrom, which is very similar to the original calcium before bond length. This 3 strontium bond length becomes 2.6 angstrom, which is not much, but is longer than the original 2.4 angstrom in the calcium PS2. So this suggests that W3, the position of W3 is more affected by the replacement of strontium with for calcium. And these changes may have caused decrease in the water splitting activity, which suggests that water-3, W3, is the water molecule that has an important role in water splitting. And based on this, we can suggest that water-3 provides the second oxygen for O bond formation. So this O bond formation may occur between water-3 and O5. So we can propose a reaction mechanism based on this, which is here, and this is basically this mechanism is proposed that W3 moves closer to O5 in some intermediate structure, intermediate state, to form an O bond. Then this O bond, this O oxygen species are cut out from the cluster to give rise to oxygen molecule and to be evolved from. Then in the final step, O5 position becomes empty and a new water molecule comes in to occupy the O5. And this completes the whole reaction cycle. So the essence of this reaction mechanism is that W3 moves or attacks O5 to form an O bond. And I have to say, this is a proposal based on our structure analysis of native PS2 and the structure replaced PS2. And we have to, in order to confirm this mechanism, we have to analyze some intermediate state, the structure of some of the intermediate states, and we have not been able to analyze these intermediate states. So we are now trying to analyze these structures of the intermediate states in order to confirm this mechanism. Okay, so there are still some questions left regarding the exact mechanism of water splitting. For example, when and where are the two substrate waters found? And the exact structure changes accompanying the state transitions and the site of proton release. So I will leave these topics and now move slightly to some the protein parts, the function and the laws of the protein parts, because PS2 is a very large protein complex, and the catalyst is only bound to the protein matrix, and this catalyst cannot be isolated. It is only maintained within the protein complex. And the immediate environment of the catalyst is provided by its direct ligands from amino acid residues. And these are the structures the electron density we obtained for the surrounding protein amino acid residues and the water molecules. As you can see, we can clearly determine the structure of the protein and the water molecules. So the ligands of the metal cluster are provided by, in total, 7 amino acid residues. And most of them are carboxylate residues, and only one is from histidine residue. What is more interesting is that there are several additional residues and the water molecules surrounding this cluster, which do not coordinate to the metal ions directly, but they provide hydrogen bond to oxygens. And this histidine residue is hydrogen bonded to oxygen 3, O3 here, for example, and this arginine residue is hydrogen bonded to 2 oxygen atoms, O2 and O4. And then there are several water molecules to form hydrogen bonds to the oxo bridges. And these hydrogen bonds are also very important in order to maintain the structure of the catalyst. Because if you imagine there's no hydrogen bonds here, the bonds between manganese and oxygen will become very strong, like typical manganese oxygen bonds in organic manganese oxides. And if these bonds are very strong, then the cluster will become very strong and stable, and the cluster will not be able to undergo structure changes. So these hydrogen bonds play a very important role to pull out the oxygen atoms to the outside of the cluster in order to make the bonds between oxygen and manganese longer than those typical manganese oxygen bonds in organic manganese oxide. So these hydrogen bonds function to destabilize or maintain the unstable structure or maintain the flexible structure of the cluster. And in fact, if we remove this hydrogen bonds, then the cluster will become strong and unable to catalyze water splitting. And this has been confirmed by site direct metagenesis to change one of these amino residues. And if we change any one of these amino residues, then the cluster, the activity of water splitting will be lost. Then there is another amino acid residue here. This is a tyrosine residue, as I mentioned. And this tyrosine residue functions to mediate electron transfer between the metal cluster, manganese cluster, and the chlorophyll, which is we call the reaction center chlorophyll here. And what was interesting we found in the structure is that in addition to the electron transfer function for this tyrosine residue, it is in a position for a hydrogen bond network connecting this cluster to the outer surface of the proton complex. Because, as I mentioned, the manganese cluster is located in here, and water splitting happens here. When water splitting occurs, there are protons produced here. And this reaction has a very high activity, and protons, the amount of protons produced is very large. So the protons must be pumped out to the protein surface through the hydrophilic region of protein region. Otherwise, if some of the protons cannot be pumped out and left here, it will lower the pH of this microregion here, and this will destroy the catalyst and destroy the whole protein complex. And we have calculated that the proton, if the proton is not pumped out and just diffused passively, the rate of diffusion, proton diffusion, is much lower than what is required to remove protons produced from here, this site. Because the proton diffusion in the protein complex, in the hydrophilic protein regions, is very slow. And this is by far can satisfy the removal of protons produced by water splitting. So there must be some proton channel for transfer protons out of this region, and this proton channel must be hydrogen bonding networks formed by amino acid bases and water molecules. And what we found is one of the protein hydrogen bonding networks is here. Starts from the all this oxygen involving complex here. And this is the tyrosine residue, Y161 here. And through several residues and several water molecules, and this proton network, hydrogen bonding network, goes out to the surface of the protein complex, to the solution. So this hydrogen bonding network is maintained by this tyrosine residue and required for pumping out of protons to the outside solution of the proton complex. And if you see so this starts from this tyrosine residue, and each pair of amino acid residues and water molecules, you can see the distance between them are all within the hydrogen bonding distance. So they form a very well-defined hydrogen bonding network. And because this network, mediated by this tyrosine residue, and this tyrosine residue functions also in electron transfer, so this proton path is called proton-coupled electron transfer path. Okay, there's another well-defined proton network, hydrogen bonding network, which is maintained by a chloride ion here. So it also starts from the manganese ion cluster, so through several amino acid residues and water molecules, and then also goes out to the surface of the protein complex. And this is maintained by this chloride ion. And these are the residues and water molecules participating in this hydrogen bonding network. So this is the second hydrogen bonding network required for proton removal from the reaction site. Finally, I should stop, but there is the chromophores, which function to absorb light energy. And there are, in addition to these 4 chromophores in the middle, because this is a very large protein complex, there are more than 30 chromophores, 29 chromophores in the 2 sides of the 4 chromophores in the middle. So they are surrounding these 4 chromophores, and all of these chromophores absorb light energy. But the energy absorbed by these chromophores in the 2 sides do not produce charge separation state, do not eject electron. So instead, so what the energy is absorbed, the energy absorbed by these chromophores and these chromophores are transferred to these 4 chromophores in the middle in order to help these chromophores to eject the electron more efficiently. So these chromophores we call antenna chromophores, just like antenna in television. They function to absorb light energy to transfer them into the electrocentric middle of the chromophores and to help electron transfer more efficiently. And there are also unique features for the arrangement of these chromophores in order to harvest energy efficiently. So this and these chromophores, one of the features, if we look at from the side of the membrane, these chromophores are organized, are located in 2 layers. One layer from the upside of the membrane and one from the lower side of the membrane. And within each layer of these 2 layers, the chromophores are located close with each other. Close means that the distance between each chromophore in this layer is shorter than 10 angstrom. So the energy they absorb can be very efficiently equilibrated within one layer. And the energy absorbed by any one of the chromophore can be transferred very fast within this layer or within this layer. And between these 2 layers, there is only one chromophore. in the middle. And this one chlorophyll so functions to transfer energy from one layer to the other layer. And this chlorophyll, because it is located in the middle of the membrane, it cannot absorb light energy directly from outside, but just a function to transfer energy between the two layers. And between these two sides, the energy are absorbed by this chlorophylls and this chlorophylls and this reaction center chlorophyll. There are also two chlorophylls here and here. And the energy absorbed by these chlorophylls and these chlorophylls are transferred to the reaction center chlorophylls through these two chlorophylls. So they are not transferred randomly, but through only these two chlorophylls, in order to ensure that the energy is transferred only from this direction, not from the opposite direction. Otherwise, if you have many chlorophylls surrounding this reaction center, the energy can go this way, but also go back to the other way. And this will decrease the energy absorption and transfer efficiency. So these are also the features for the organization of this pigment in this protein complex. And these features are optimized through a long time of evolution, probably 1 billion of years. So this is the organism that found the solution to efficiently absorb light, harvest light energy, and catalyze water splitting. Okay, this. And very happy that UCC has just introduced. We published our results in 2011, and we're lucky that Science Journal selected this our structure as one of the breakthroughs in 2011. And we are very happy. Science comment on our structure is that this structure isn't just essential for life. We also hold the key to a source of clean energy. As I mentioned, if we can synthesize catalyst like manganese cluster in PS2 to split the water using sunlight, probably we can obtain clean energy from sunlight in the water. So PS2 structure offers a window into a catalyst that is essential not only for past and present life on Earth, but also perhaps for the future of civilization. Because the oil and most of the energy we use today depends on the photosynthesis in the past. And the oil is produced from organic substances which are produced by photosynthesis, photosynthetic organisms in the past and also present, but probably also of future civilization of future. So we are very happy to see this. And I should introduce my co-workers, the structure analysis. My lab purified protein, made crystal, and collect X-radiating spin 8. The structure analysis was done in collaboration with Kamiya-san in Osaka City.